Thank you. So we've been talking about mostly Wasserstein gradient flows, and the canonical example of that was the diffusion equation, which, as we saw, is the Wasserstein gradient flow of an entropy. And Tuesday, we talked about entropy and why we can, how we can interpret entropy as a measure of degeneracy that is inherent in the structure of an empirical measure. Degeneracy meaning that there is somehow lack of information in going from a loss of information in going from a sequence of particle positions to a sum of delta functions. And one way to see that is that the numbering is gone. And so that degeneracy, the loss of information, comes back as an entropy. And as we'll see later on, it gives you a bias in certain directions exactly because of that degeneracy. So today I want to start talking about what the Wasserstein gradient, what the Wasserstein part has to do with this, and so one of my main claims will be, I'd like to write this theorem, but there's nothing I can prove. This is just philosophy, so I have to rephrase it as a claim, unfortunately. So my claim is that the Wasserstein metric, which I'll abbreviate as WM, it characterizes the mobility of Brownian particles once you do the same thing as here, once you transform them to an empirical measure. So again, we have empirical measures arising here. And I will only be able to touch on this today. I mean, most of this claim will come tomorrow. But I can do something else today, which somehow is part of this story. Think of it as a subclaim, which is that maybe one way to think about the Wasserstein metric is that it's, I guess the best way to say is that it is the same as Euclidean multi-particle geometry after, again, transform to empirical measures. So, occurrence number 3, empirical measures are important, as you have probably realized by now. And so, let's start making the second one precise. That at least I can do today. Let me just ask, to whom does this actually mean anything? You've heard me too often. To whom does this mean anything? No? Yes? No? Not yet? Okay. So that's both good and bad, I guess. Okay. Anyway, so let's look at this business. So the reason why this is somehow simpler than this is that I can forget about stochastics for a moment if I only talk about geometry. So forget about stochastics, forget about Brownian particles, just talk about geometry of spaces, nothing else. So this is somehow a slightly simpler setup. Okay, So let's. I talk here everywhere about a transform to empirical measure. So let's write that explicitly. We define a transform operator En that takes n copies of my space Rd and gives me gives me a probability measure on Rd by the formula. So I'm going to write this thing as. So now I'm going to use vector notation for the fact that I have n copy vectors. So that's what the arrow is going to mean. This thing is defined to be 1 over n times the sum of I1 to n of delta x psi I. So my vector psi is a vector with components psi1, psi n in Rnd, which I think of as Rd to the power n. Right? So this is what I mean by a transform or a transformation to empirical measures. I take an n vector of elements in Rd and I map them to a probability measure by this formula. Now, one thing you can see right away, as we talked last time, is that indeed the numbering is gone. If I do a permutation of the indices I, then this object here will change because I'm changing the values. But this thing will not change because I'm just adding them up. So it makes sense to look at the following object, saying I take Rnd, but now I symmetrize it. So I'm going to define a metric space consisting of a set Rnd symmetrized, which is Rnd, where I identify with each other all permutations of the same indices. So in other words, I divide out by permutations of n objects, the n positions. So Sn is the set of permutations of n objects. And so this is by definition the sets of equivalence classes of n vectors that are, let's say, equivalent on with each other, so they're equal to each other after some permutation. Now, I started with a nice Euclidean space. Of course, when I do this trick, I lose my Euclidean structure. That's too bad. But my Euclidean space is also a metric space, and metric space properties I keep under going to equivalence classes, provided I define the right metric. That's what D is for. So my D between two of these objects. Yes. That's a good point. So what should we do instead of D? Capital D? Yeah? Okay. It's true that I don't think I'm going to ever raise something to the power of the metric. That's not going to happen. So. Okay, so I define my, and quickly I will place D by something else so that maybe it's not too bad. So I'm going to define the metric by its square and say the square is 1 over n times the infimum over, that's what you have to do with this kind of, you go from one metric space to a quotient metric space, you have to take the infimum over your quotient. So I take the infimum over all permutations of my original metric, which is psi I minus eta, and after permutation, so eta sigma I. My original metric was just a Euclidean metric, and so I take the quotient over all my permutations. That gives me a new metric on my on this symmetric space. Okay. And I like the 1 over n because it'll make this thing later on numerically identical to the Wasserstein distance. Without the 1 over n. Oh, there's a sum. Where does the sum go? Yes, sorry. Yeah. Okay. Yeah, so far so good. So now there's a very simple lemma, which says the following: that if I think of if I think of En as mapping my R and D sim D to probability spaces with the Wasserstein distance, order 2. And I mean, formally, if I want to define my Wasserstein distance, I have to look at probability measures with finite second moments. That's fine because n is finite, and so this is going to be always going to have finite second moments. So this the image of En lies in the subset of P2. So my claim is this is an isometry. I will do the calculation in a moment, but really that is extremely interesting because it tells you that, in some sense, the interpretation of the Wasserstein distance on RD is that it's the same as this Euclidean distance after you factorized out the permutation, and that's exactly the statement that I'm making here, at least part of it, saying that the distance that you measure when you measure Wasserstein distance, order 2, really is the same as if you were measuring Euclidean distance for points, except for the fact that, of course, the Wasserstein 2 distance is defined on a bigger set than the image of En. Image of En is just n delta functions with specific weights 1 over n. And the Wasserstein 2 distance is defined on a much larger set. But morally, in terms of interpretation, what it's telling you is that the same Euclidean structure that you have on n copies of RD comes back, at least in some form, through this mapping to empirical measures in the form of W2. So let's just briefly prove this. So we just
instead of starting with the Wasserstein metric, you just looked at you assumed that the map were an isometry, and you looked at the metric.
I don't know what you're asking.
Well, yes, but this is whether you would get the Wasserstein metric, by just taking a map and the isometry on the space of measures that is induced by this distance and this. That is his unique case.
Oh yeah, I mean, he thinks the answer is yes. I still don't understand exactly what you're asking, but if he says he's yes, then I'm happy to go there. You can't have two different isometries to different objects, to intrinsically different objects. But then, then there's a third isometry between the other, right? Yeah. So the union over n of the images is dense. So the union over n of En of RND or IRD symmetry doesn't matter. This is dense in P2, W2. Yeah. Of course, for fixed n, it can't be because it's just a bunch of delta functions. The proof of this statement is just a question of writing a couple of things out. So W2 distance squared of two of these objects. So in other words, the distance in the target space is equal to the infimum over all couplings between these two objects of the integral of x minus y squared gamma dx dy, And there's a simple argument that shows that it's okay to limit yourself to gammas that are of the form gamma sigma, where sigma is a perturbation, and where so gamma sigma of dx dy is equal to the 1 over n times the sum of a delta function at our product point. So I guess I better get rid of this. Product point psi I eta sigma I. So you limit yourself to pure permutations, and that's because of the linearity of this structure. This turns out to be enough for this what you do, because the whole one is are linear combinations of this thing, and this is linear. So it's enough to limit yourself to these ones, gamma sigma. And then once you have this is actually exactly the same as the one that's written over here. Just writing out explicitly the fact that sigma delta is gamma sigma is a bunch of delta functions. This is actually exactly the same as the distance between psi and eta square. I mean, it's practically at the level of just manipulating formulas. The only non-trivial one is this one. So this follows from remarking that because this is linear, if you have two minimizers, then the linear combinations are also minimizers, and so it means that you can restrict yourself to looking at extremal points of the set gamma, and the extremal points are this one. Yeah. I mean yeah. So what before? I'm telling you now. I mean, that's the best I can do. So I'm sure that there are certain people in this business who consider this to be trivial, which, of course, once you've recognized that it is, and therefore never bothered to write it down. I would be highly surprised if Robert McCann didn't really understand this when he was working on this interpolation convexity concept. So talking about interpolation convexity, yes, go ahead.
So this never would also be true for any convex closed branch, I guess.
Provided you make the appropriate replacements, yes. But you want something that starts out its life as a distance, essentially. Yeah.
Yeah, but I mean, if it's a convex function of the distance, then I think it's...
A convex function of the distance would do it, yes.
But in general, I think it's not.
For general costs, you mean? No, I mean, for general costs, of course. I mean, the reason why this works nicely is that both objects are metrics, and that has to do with the fact that you're starting with a metric over there. An arbitrary cost function doesn't need to be a metric on the original Euclidean space.
Okay, so what would be the exact criteria for which closed functions this happens to do?
I would have to think about that. We can do that later if you want. But we can do that later if you want. I don't know. I mean, the reason for being very specific and not even doing powers p, just only doing powers 2, has everything to do with the fact that there's a very important physical reason for looking at power 2. We'll talk about that in a moment. I mean, another way of saying it is Brownian motion gives you 2 and nothing else. That's another way of saying why 2 is special. There's also, of course, there's more. Wait a minute, there's more. It's also true, of course, that in power 2, the RND is a Hilbert space, and so we can use inner product structures, which is also something that vanishes as soon as you leave the square. But so talking about displacement convexity, so in some sense from this argument it becomes obvious why shortest paths in Wasserstein distance should be straight lines in terms of their underlying particles, because shortest paths in the original RND are straight lines, And so, so it becomes completely natural to make an interpolation along these things with constant speed in a straight line. And so by this identity, for finite n, somehow it becomes very reasonable that the same should be true in the limit of n to infinity, if you want. But that aspect, of course, would also be the same for various other distances. They would also have the property that you make constant speed connections. Now, as I said, the nice thing about the square is that you have in the original space you have an inner product structure, which a priori would not at all be clear that you have anything like it in Wasserstein distance, but it turns out you do. And so let's have a look at this. So this is kind of part 2 of my subclaim, because what we just did is we showed that the Wasserstein distance can be interpreted as a multiparticle Euclidean distance, provided you make the transformation. But that this goes further than what we just saw. We've seen now that distances transform this way, but you can also look at inner products. And so on flat spaces, these things are called inner products, but on Riemann manifolds, it's typically called something like a metric tensor. The same thing, really. And so now, if we start in the original space Rnd, we would have an inner product of the form. We take a vector in Rnd, and we have an inner product of the form. Let me just write it like this. If I use the same scaling, there's a 1 over n times the sum over inner products in Rd, sum over I. I mean, it's a little bit weird writing it like this, because this is the sum over components, and this is sum over components, but still, sometimes it's useful to write it like this. Because this thing here, I can further rewrite as the integral over En of psi as a function of x times a v as a function of x and a w as a function of x, if I decide to define my v and w to have the property that whenever I evaluate them at one of the points given by psi, I get the corresponding I mean, by writing things in this way, I haven't done anything. I've just kind of written the same object in a different form. There is something funny happening, which is that I started out here by saying that I was looking at a v and a w. It was not quite obvious what my psi would be, and by the time I've arrived here, suddenly I have a psi. I mean, so you have to ask the question what exactly is happening, and the idea is that going back is maybe more logical. If I have a psi, then I know where my points are. Now, associated with my points in Euclidean ideas, you can make perturbations of points which are vectors in the tangent space of Euclidean space, which is the same Euclidean space again. So those are the v's and the w interpreted as potential perturbations of my positions of my points. That's exactly what this says in some sense. And then the rest is just formulation. I mean, so this level, this is just kind of writing a couple of formulas down. But the point is that because of this formula here, if you indeed look at the density of these things in P2, then this measure here should play the role of an arbitrary element of P2. And you would like then to interpret V and W as potential perturbations of that measure. And so this suggests that that P2 W2 might have an inner product structure, at least formal, of the form rho times V times W integrated over Rd. Meaning that if you sit at a point rho, like sitting at the point psi, if you sit at a point rho and you think of V of W as perturbations of the particles represented by rho, then this could be an inner product. And so what exactly that means, you still need to think about. For instance, you need to think about what it means that V v is a perturbation of rho. And so the way to think about that is to say that if I would have a curve, t to rho t, which is represented as that the particles move with velocity v, then the corresponding equation satisfied by rho t is exactly this one. This is the equation that says that whatever particles rho represents are convected by a velocity v. Yes. No, I'm thinking. So to one extent, yes. I mean, you think the way Riemannian geometry works is you fix your point on your manifold. You have a tangent plane on your manifold. On the tangent plane, you have a metric tensor. It's a local Euclidean space. But the interpretation of your tangent vector is actually as a potential velocity vector of a moving point, right? And this is the way you should think about it. So there are two things happening at the same time now. He was first. So say it again. Fixed with respect to what? Yes, that's the right way to think about it. So, I mean, one other way of doing the same thing would be to say, okay, so what would be one way of doing the same thing? You look at. Oh, okay, yeah. So I mean, the thing is, at the end of the day, whatever I stick in here has to be defined en almost everywhere. And then I okay. This alleviates the confusion. This is good. Okay. Okay. Good. It seems to be. I mean, all this is extremely hand-wavy, and hopefully this will be a rigorous theorem. Well, you know, if you think of psi in your symmetric space, then you know it completely. No. But then, of course, for the left-hand side, that's fine. For defining V bar, I don't need to know which number I. Yeah. So V has to have the same numbering as psi. Yes, they have in that sense have to be adapted to each other. Yeah.
So somehow you give this psi as an additional information.
No.
In case of a lemma, right? And on the lemma you symmetrize over the labeling, right?
Yes.
So it's something that you forget is I.
Yes.
And here somehow you stop.
Well, here you should think really that there's at the back of this you assume one of these objects without the symmetry, and you decide to use the same numbering for each three. Of course, you can then decide to renumber. Well, this kind of, I was hoping this would kind of make clear what I'm going to write down next, but maybe it's not making anything clearer. But the idea of the. Okay. Let's continue. Maybe that clears things up. Right? So, so somehow, I mean, if you think about this as if it were a Riemannian manifold, you would say this is the velocity of my, so the velocity vector of my point, and it's related to something that I think of a velocity field in RD by the fact that this is equal to minus that. That's the relationship that kind of connects the velocity vector of points on one hand with my kind of time derivative of my state on the other. And so this is what we somehow want to do. We would like to say that I can write something of this form in terms of the dt rho, and that can only be done in some sense in an abstract way, and that's what we're going to do now. If I can find my notes. Yes, here we are. So this this were Ambrosio, Gili, and Savary in their book in 2005, and later edition 2008, who realized how to do this in a good way. I'll only get an infinitesimal part of what they say in their book. And the point is, well, one of the points is that to start with, this is not going to work as it stands. And the reason for that is that in this equation, V is underdetermined. If I fix myself this object, then I can add to V something for which the divergence of rho times that something is 0. And so essentially zero divergence vector field. And so that means that this thing would also suffer from the same problem. So that's not going to work. So for that reason, we introduce a new object that I'm going to call H rho for rho in P2. And H rho is what you get when you take gradients of nice functions and you close this in a set L2 with measure rho. That is so all these objects lie in L2 rho, and L2 rho is a nice Hilbert space. So its closure is again a Hilbert space with the same inner product as the original L2 rho space had. So this is a nice Hilbert space, a subset of L2 rho. And so then we define again for rho in P2, we define a set that I call a tangent set space of a rho. Sometimes yes, and sometimes no. And I once asked Giuseppe Savary the question when he knows which is which, and he says he doesn't. I mean, there are cases where they understand that there are kind of differences, and there are cases where it's not. So it's complicated. This is the easiest way to think about it. This is the easiest way to think about it. The closure of the gradients of smooth functions.
So in which case would it be different from the set of gradients of solid functions?
Oh, so the point is that if your rho is singular, then there are large bits where basically anything can happen, right? You see what I mean? Because then you can take anything for this. And it doesn't, I mean, then you don't even have to have, really, I mean, if your rho really consists of a bunch of points, then it's only the values at that point that make a difference. And so anything happen, I mean, anything could happen in between. So that's the reason why it's complicated. Think about it later.
You want an explicit example, take square root of rho and square root of x in 1D continued by 0, then the gradient is 1 over square x. If you square it, it's not an L2, so you cannot approximate by L2. But it's in L2 with respect to any rho which has a 0 at 0 as its mean. Okay, so anything that lifts off to something from 0 is not in the space, even when the domain is just an interval on which it's positive. Because it can be general in a bad way or something.
But I think, I mean, for instance, the other extreme is the case where you're working on a bounded domain and your rho is bounded from below and from above, maybe to make things nice. In that case, you would be right. It would be exactly the same as the usual subleft class.
And why is it more convenient to work with this space than with the solid space?
I mean, sometimes you have that, right? That you do the mathematics, and suddenly the mathematics is telling you, I don't care that you already know about Sobolev spaces or BV spaces or whatever. The mathematics is telling you, this is the thing you want. And this is a kind of example. I have no better answer than that. So, okay. So I define a tangent space to be exactly what you get. Yeah, go ahead. You want to test with phi. You want to test with something like phi. Yeah, exactly. Yeah. Yeah. I mean, one of the exercises we'll do today is exactly about this, and then you can kind of play around with that yourself and convince yourself this is actually a good choice. Anyway, so going back to the tangent. The tangent is to say we're going to take V not in a very large class, but simply in this H row. So the tangent is by definition all things of the form minus the divergence of rho. So I know, I mean, it's a tangent at rho, so I know what rho is, of some V where V lives in H row. And for those who know Ambrosio Gili Savare sufficiently well, I have to warn them right away, this is not the same definition that they consider, because they consider this thing to be the tangent space, whilst I consider, so they consider the V to be the tangent space, but I consider the time drift of rho to be the tangent space. Just depends what you're using it for. It's mathematically equivalent, it's just a question of notation. Anyway, so once you have that, then now you can say, okay, if I have two elements S1 and S2 in this tangent space, at the same point rho, I have two elements of the same the tangent space at the same point rho, and so then we know that they are coupled to some Vi in H rho, right? Then I define an inner product S1, S2 minus 1 rho. I define this on this tangent space by saying exactly the thing we have over here. Rho times V1 times V2. And so, I mean, as I said, one of the insights here is that the indeterminacy of V has to be addressed. That's what you do by limiting yourself to the class H rho. But then once you've done that, then indeed you can think of the inner product of two of these objects by writing out this inner product of the corresponding flow fields V. And of course, once you have an inner product, you have a corresponding norm, which is simply this thing. So that's the integral of rho times V squared if S plus the divergence of rho V equals 0 and V equals H rho, right? So the notation minus 1 comma rho, the comma rho means this thing depends on where you are. And it depends in a million ways on where you are. It depends because it's defined on a set rho, which depends on where you are, because it's a closure in L2 rho. And then the differential operator with a rho. So, I mean, in a million ways, this thing depends on where you are. And the minus 1 is that it's actually, you can think of it as a negative Sobolev norm, as a weighted H minus 1 norm. Yeah. Oh, sorry. Yes, I should have said that. That's a good point. So, so provided you limit yourself to H rho, now the P is unique. And that's also one of the exercises I want to put later. believe this. So coming back to my subclaim here, nothing. Well, I guess well, are you asking what is the contribution of Ambrosio, Gili, Savary, or? Okay, so I guess, I mean, the stupid answer, of course, is read the book, but okay, that is, so, I mean, there are lots and lots of contributions that came from those three guys. Specifically for this very specific question, I think the important thing that they realized was that the right way to think about it is A, to think about absolutely continuous curves in this metric space, in the Wasserstein metric space, which is something that's nicely defined without any form of differentiation. And then show that you do have something like the length of a derivative in this object, not the metric slope, but you know what I mean? Lost the name for the moment. And then to show that for WP Wasserstein spaces, that if you have a curve that is absolutely continuous in this WP space, then this local derivative, length of derivative object can be described in terms of something that looks like this within that space. And yeah, and that's somehow there's a one-to-one, there's a one-to-one mapping between absolutely continuous curves on one hand and curves of vectors v in h rho on the other.
I think one advantage also is that this summary is more safe. If you pass through singular space, for instance, this is the way how you should do it.
I don't know what a singular space is.
Metric space, optimal transformative space, and so on. So the a priori you don't have a nice Henry formula.
Yes, they essentially never use that. Yeah. So this is exactly the case that I am not interested in, because I mean, in everything I do here, this is very much inspired by, for instance, the behavior of Brownian motion, and that somehow dictates Euclidean geometry, at least locally. Oh yeah. So coming back to here, I was claiming that the Wasserstein metric characterizes some, or kind of describes some kind of Euclidean multiparticle geometry. And so the interesting thing is that in this case, for p equals 2, it describes not only the level of distances, but also the level of inner products. And there is, in some well-defined sense, there's something that you can think of as an inner product, which is directly inherited from the inner product structure of Rd. Right? Okay. Yes. So just to answer your question and write down my first exercise. I didn't do any paper this time, so I'm going to write exercises on the board for those who are interested. So there's a nice lemma that says, given, and this lemma will be an exercise, given an S in the tangent space of rho, we have a couple of equalities. So the thing that's over there, minus 1 rho 2, is equal to the infimum of the integral of rho v squared among all v in h rho, such that S equals minus the divergence of rho v. And part 2 would be the fact that this is unique. That's your question. And part 3 would be the fact that this infimum is actually the same as the infimum over, let's say, rho w, such that w is in the whole of L2 rho, but still satisfies the same. And so, so the first one has the benefit that you have a very natural extension to S's which are outside of the tangent, which is kind of convenient because if the set is empty, you make it plus infinity. And the interesting thing about the connection between these two is that it says that somehow the reason why you're restricting yourself to H rho has everything to do with the fact that these two infima are the same. The fact that you can restrict yourself to H2 rho is exactly related to, and this is the kind of place where the structure of H2 actually comes in very nicely to show this is the case. And so for those who want to think about this, the simplest way that I know to do this, which is very simple, is to decompose L2 orthogonally, and then everything drops out. Yeah. Okay. Yeah. So, I mean, we were doing all this because we want to understand why we had why we see Wasserstein gradient flows. And in the case of the entropy, my answer to the question why the entropy drives an evolution came from stochastics. And so let me leave this on the board. And so I want to do the same. And now, very briefly, in the last couple of minutes, talk about stochastics, about how this connects up, and then I'll do the real stuff tomorrow. So I claim that the interpretation of Wasserstein metric, one of the interpretations is that it characterizes the mobility of Brownian particles. So let's make a couple of Brownian particles, x1, x2, iid Brownian particles. And for the probabilist amongst us, my generator is always the Laplacian, not 1/2 the Laplacian. That's why I'm saying it. Was this Gauss's choice? So he put the 1/2 and got the 1/2 Laplacian as a diffusion equation. Yeah. I'm not quite sure that I'm convinced that that was a worse choice. Maybe that was a... Yeah, but the Legendre transform of the Gaussian is the Gaussian, and that's also good, right? Yeah. Yeah. Okay. Anyway, so let me just check. Who doesn't know what I mean when I say a Brownian particle? Can I see hands for those who do not know what I mean when I say Brownian particle? Jero wants to know the details. Okay, so then I'll just state the theorem right away, and then we can go to the exercise. So, so again, I look at the empirical measure of these things, which now is a time-dependent empirical measure. So if you want, it's the same as En applied to the vector of x at time t. And so I'm guessing that this might even be known before, but the oldest version that I know is Dorson and Gettner. They say something more than this, but for this specific situation, it gives you a statement that the probability that rho n behaves like a rho on some time interval 0t, conditioned on that the initial value is exactly something that I choose myself. So let me say rho at time t equals 0 is some rho 0. This has a large deviation principle, which is e to the power minus n I of rho rho being the trial variable in here. And so what is I of rho? I of rho is equal to 1/4 integral from 0 to t. I'm working on time interval 0 t of exactly this norm of dt rho minus time t minus Laplacian rho time t, and this minus 1 rho t norm dt. And then provided rho at time 0 indeed is equal to my rho 0. I mean, there's a later paper by Kipnis and Lundin, but no, Kipnis and Ola, but which does this, but it's later. I'm not quite sure whether that means that it was actually written earlier or not. Okay. Anyway, so what does this tell you? It tells us lots of things that we're going to discuss tomorrow in much more detail. But for the moment, just let's look at it at a superficial level. It says that I can ask the question whether rho n looks like a solution of the diffusion equation, in which case this would be 0. And I can ask the question whether it looks like something that is not a solution of the diffusion equation. The interesting case is the second one. So I now take rho to be not a solution of the diffusion equation. I ask the question, what's the chance that rho n does something like rho, which is not a solution of the diffusion equation? Then the answer is, well, that's characterized by this functional. And so what it really is telling you is that the deviation from being a solution of the diffusion equation, the defect, you would call it in numerical analysis, is measured exactly in this Wasserstein metric tensor norm. And that has a whole bunch of consequences and interpretations that I'm going to be very happy to discuss with you tomorrow. And I think now it's a good time to think about other things. So I wrote down one exercise over there. There's another exercise which I can write below that, which is something that I discussed too fast on Monday, which is the fact that the Benamou-Brenier formula is the same as what you get when losing this thing. So let's say show that W2 distance between a rho 1, which by Benamou-Brenier is the same as the infimum of the integral from 0 to t, integral of Rd of rho times v squared under the condition that dt rho t plus divergence rho t v t. So these are time-dependent, position-dependent objects equals 0, and such that rho t at time 0 and 1 equals rho 0 and 1, the objects that are here inside here. But this is indeed the same as the infimum. So this is the infimum over rho and v, now infimum over curves rho 0 to t of dt rho t minus 1 rho squared dt under the same condition. Not so much this one, but that one. And both are fairly straightforward. So I suggest we leave it here and yeah, once you get the details, yeah. But it's good to work it out and to see it.
So very fun. If you like in respect to the Ambrosio sovereignty norm, doesn't give you more intuition like this? I know it's again it's equivalent from the top, but like then you see what happens with the vector field. Like now, like okay, I know that this measures the distance from what Laplacian tells you.
Yeah.
But I don't understand what Laplacian tells me.
No, okay. So we'll talk about this much more tomorrow. I mean, so the thing about intuition is, of course, that depending on which direction you want to be going, you'll be using different formulas. I mean, we do this all in our proofs, right? I mean, you want to go in a certain direction, so the first thing you do is start writing whatever you're looking at in something that really looks like the direction you're going in. So I think, I mean, the right way to think about it is it depends on which way you want to be going afterwards. And in my case, I want to go somewhere where this is a very natural way of writing.